In last week's video, I described a crystal as an infinite ordered array of atoms. Its structure can be described by identifying the smallest repeating unit, or unit cell. The unit cell connects lattice points, which are all identical to each other regardless of where they are in the crystal. So here I've drawn a collection of lattice points, and here is the corresponding unit cell. Now in today's video, I want to show that a crystal can also be described as a collection of infinite parallel lattice planes that pass through these lattice points. This will probably seem like an abstract concept right now, but just bear with me. As we'll see in Monday's lecture, this description of a crystal is the basis for the experimental technique of crystallography, which is the way we actually work out where the atoms are in crystals. This is arguably the single most powerful analytical technique in all of chemistry. Now, I'm going to simplify things to start with by rotating this picture to look directly down the z-axis, like so. This is so we can effectively work in 2 dimensions. We'll come back to the 3D case at the end. So here's a lattice plane. It runs through a set of lattice points, one of which is on the bottom left corner of the unit cell. Now we know from last week that all lattice points are identical, so there must be an equivalent plane running through the other lattice points on the unit cell. So here, and in fact through every lattice point in the whole crystal. Now note that when we complete the set in this way, every lattice point in the crystal will have one and only one plane passing through it. Now, we don't necessarily have to choose a plane that goes from one lattice point in a unit cell to another lattice point in a unit cell. I can draw a set of planes that go like this, goes through one lattice point, but then the next lattice point it hits is 2 unit cells away. That's fine. Now we apply translational symmetry, we go to the top left side of the unit cell, draw the same plane, repeat throughout the crystal. We've got a set of planes. However, we haven't still completed the set because we don't have a plane going through the bottom right and the top right lattice points of that unit cell. Like so, and like so, and those also complete and tile the entire crystal. I haven't drawn them all in, but you get the idea. Here I've chosen a lattice plane in which the lattice points are even further apart, and if we want to complete that set, we have to draw the equivalent plane through every lattice point again, like so. Note that a consequence of this is that when we choose a plane that has lattice points further and further apart from one another, then the planes themselves will be closer and closer together. Now, the next thing we want to do is define these planes. We want to come up with some classification system for them so that we know what set of planes we're talking about. In order to do that, I'm going to focus in on the central part of this picture here and just look at the planes around the unit cell itself. We classify lattice planes in terms of how they interact with the unit cell. So that unit cell has a side length A and a side length B. Now in order to identify a plane in terms of its Miller indices, we first spot the plane that passes through the origin of the unit cell. In this case that's defined as the bottom left. So I've indicated that with the blue circle. We then look at what the next nearest plane does. So that plane that's up and to the right intercepts the A-axis at this point here, which is 1/3 of the way along A. And that same plane intercepts the B-axis out here, which is 1/2 of the way along B. The intercepts with the A and B axes are therefore 1/3 and 1/2 along A and B respectively. In order to label the plane, we give it its Miller indices, and those Miller indices are just the reciprocals of the intercepts. So 1/3, 1/2 becomes 3, 2. So this set of planes have indices in 2 dimensions, 3, 2. Generically, we say that the intercepts are 1 over h and 1 over k, and the Miller indices are then h and k. And in 3 dimensions, this becomes hkl. The other thing we are interested in with respect to these planes is the distance between them. So I've indicated that here. Okay, this is the shortest distance between the planes. And that distance is defined in terms of the Miller indices. We don't have to go through the derivation, but if you look at the collection of 3 right-angled triangles involved, noting the angle between A and B is 90 degrees in this cell, you can go through Pythagoras and figure out that 1 over d squared is 3 squared over a squared plus 2 squared over b squared, where 3 and 2 are the Miller indices. We'll come back to a generic description of this at the end. I want to also show 2 other sets of lattice planes in this way in order to highlight a couple of points about Miller indices. Firstly, if I flip them like this, then I will have negative Miller indices. Now, to show what I mean by that, we take the origin, so look at the bottom left-hand corner with the blue circle again, and then let's look at the plane immediately above it. So it intercepts the a-axis at 1/3 of the way along A, same as before. Now, if we go halfway along the b-axis, we also have a plane intercepting the axis, but that's not the same plane. It has to be it's a single plane intercepting both axes. So actually, if we're using A as 1/3, what we need to do is extend that plane down until it intercepts the b-axis, and where it's actually going to intercept is at -1/2 b. So the intercepts are 1/3 and -1/2, and our Miller indices are 3 and -2. Okay, so you can have negative Miller indices and they give you the orientation of the planes. And I'm just pointing out again that we still have a fixed d spacing and it will be defined by geometry. Now here's a set of planes that I have tilted so that they are parallel to the b-axis. So we can define the Miller indices again. Let's look along the a-axis. They intercept at 1/3. That's fine. But we now need to know where that same plane intercepts the b-axis. And of course, we extend it out, but it's parallel to b. It will never intersect the b-axis. We could say that it will intercept the b-axis at infinity. And we could write that as infinity as b, or anything, divided by 0. The intercepts with a and b are therefore 1/3, as before, but also 1/0. So the Miller indices are now 3 and 0. So a Miller index of 0 means that a plane is parallel to that axis, in this case the b-axis. And of course it still has a d spacing. In this case the d spacing is trivial, it's just going to be a/3. So let's finish up back in 3 dimensions. In this series of pictures I've indicated the origin with a red dot in the bottom left hand corner, and I've drawn the nearest plane to that. So this first one we see is parallel to the x-axis and it's parallel to the y-axis. So it never cuts A or B, but it cuts the z-axis at c/2. So its Miller indices are going to be 0, 0, 2. In this case, we have a plane that cuts the x-axis at a/1, it cuts the y-axis at b/1, and it's parallel to the z-axis. So its Miller indices will be 1, 1, 0. Here in this case, we can see that the first plane does not intercept the x-axis at all in the positive direction. We would have to extend it back down, where we will find that it intercepts that axis at -a/1. It intercepts the y-axis at b/1, and it intercepts the z-axis at c/2. So its Miller indices are -1, 1, 2. Generically then, we say that the Miller indices, HKL, of a set of lattice planes are given by the point at which the first plane intercepts the axes. It intercepts the x-axis at a/h, the y-axis at b/k, and the z-axis at c/l. And the d spacing, which is the distance between nearest neighbour planes, is given trigonometrically, and in the simple case that all the angles are 90 degrees, cubic, tetragonal, orthorhombic cells, the relationship is that 1/d squared is h squared over a squared plus k squared over b squared plus l squared over c squared.